Hi everybody, welcome back to the Feynman technique. Today our goal is to show that cosecant x is equal to the sum over the integers negative and positive of negative 1 to the n over x plus pi n. All right, so to start this off, what I would like to do is recall this identity. I've gone over it many times before. I will try to remember to link to the derivation of this equation in the description. But for this video, we're going to take it for granted. And also, this is only good for t greater than 1. Okay, so next, what I'd like to do is I'd like to just split this integral at x is equal to 1. So you can see that's what I've done in my next step. So after that, let's make the substitution x is equal to 1 over u, implying dx is negative 1 over u squared du. All right. So next, I apply the substitution only on this second integral, obviously. And applying that substitution results in this. I'm literally just plugging in the results and changing the bounds of integration. So for the next step, we simplify all this junk right here and put the dummy variable back to x. So now we have this. All right, now let's recognize this, that we can express 1 over x to the t plus 1 as the sum from n equals 0 to infinity of negative 1 to the n times x to the tn. So we can replace any instance of 1 over x to the t plus 1 with that infinite sum. So that's what we'll do. You'll notice I replaced this 1 over x, or yeah, 1 over x to the t plus 1 in both integrands with its equivalent sum. And in the second sum, I brought this inside the sum since it does not depend on n. And then did a little bit of simplification to end up with this. So for the next step, what we want to do is use Fubini's theorem, since there's not going to be any problem with convergence with our stated restrictions on t anyway. So we can switch the integration and summation notations. And inside the integral, we can bring out the integrals, we can bring out anything that does not depend on x, which in both cases is just this negative 1 to the n term. Okay. So next what we do is we evaluate these definite integrals right here. And this definite integral will evaluate to 1 over, well, the antiderivative is going to be x to this minus 1 over this minus 1. And we're plugging in 0 and 1 for x. So the 0 bound goes away. The x bound just becomes, the 1 bound just becomes 1. And then we have over this minus 1. So again, evaluating those definite integrals, and we end up with this. So the next step, basically, oops, what did I do? Sorry about that. So the next step, what I did is I subtracted 1 from all the n's, from all our a sub n's, basically. And then I compensated for that by adding 1 to the index. Why does that keep happening? Okay, now you'll notice on this sum, what I did now is I said, well, if this sum is true, can't we just, let's start n at negative infinity, or we could start it at negative 1 and then count down to negative infinity, as long as we took the negative of all our n's inside of our a sub n. So this is what we end up getting right here if we do that. And then for the next step, you'll notice all I did was factor out that -1. So now look, we have this sum, which goes from -infinity to -1, and then we pick it right back up at 0 and then all the way up to +infinity. So we can just combine them all into one infinite sum. This is not the stand. Typically, this is not what you see. We usually don't start our sums at -infinity, but you can. Anyway, so now we have this identity, and now it's simply a matter of letting t equal pi over x. And if we do that, if we plug in t is equal to pi over x, and replace all our instances of t with pi over x, we end up with this. And then in the next step, all we do is multiply the top. Sorry, we do a little bit of simplification. You'll notice this is just going to simplify to x, as is this. And in this one, all we do is multiply the top and the bottom by x. And now we have this. And for our final step, we simply divide both sides by x to arrive at our desired identity. All right, guys, I hope you enjoyed that, and we will see you next time.